Hi everyone, welcome to ETA. Now this is where we bring you the best in maths and physical sciences. But today I'm only going to be focusing on physical sciences. I'm going to be doing vectors, Newton's law, as well as universal gravitational law, which is also one of Newton's laws. So without much waste of time, let me start with the topics. Vectors. Vectors. Okay. Now, what are vectors? Vectors are scientific quantities which has magnitude and direction. Okay, let me give examples. Speed. Speed is not a vector. Distance, not a vector. What else? Yeah, we can think of many examples. Okay, what are vectors? Velocity is a vector. Displacement is a vector. So each and every time we talk about vectors, we're gonna talk about a magnitude and a direction. Also, energy is not a vector. Mass is not a vector. So anything that is not a vector is a scalar. It's called a scalar. Okay, in case if you get it in the exam. Something which is not a vector is not a scalar. Is a scalar. Okay, so I'm gonna give a very nice example of how vectors are. So vectors are always represented by Cartesian. They have directions, so they need to be put in a position graph. So let's say for instance, I have three forces which are pointing in that direction, and each of those forces are 3 newtons. And let me place another one here. Same direction, same magnitude. All these three forces the same. In the world of vector. Why do I say so? The direction is the same. They are going towards the same direction. The magnitude is the same, but they are at different positions. Nobody cares. As long as they have the same magnitude and the direction, they are the same. These are the same vectors. Okay, let's say this is x, If this is x and this is y, so minus 2 minus 2 2. Okay, that's about it. So let's talk about resultant force. But before we talk about resultant forces, we need to talk about Newton's laws of motion. We're going to talk about Newton's law of motion. A resultant force, it is the sum of all forces. Okay, let's talk about Newton's laws. Okay, the first law states that a body will remain at rest or continue to move unless a resultant force acts on it. What does this mean? It means a body which is just resting or a body which is moving at a constant velocity. They are the same in terms of Newton's law. It means acceleration is zero. That's Newton's first law. It talks about acceleration of zero. There's no change in velocity. If you are moving at a constant velocity or if you are resting, it is one and the same thing. The same thing in life. If in life you decide to just to move in the same way that you have been moving, you are the same as someone who's just sitting at home. If you have been doing one and the same thing without any resultant difference or effective difference, you are the same as someone who's just sitting at home. So there must be change. There must be change in velocity in order for us to have a resultant force. Now, let's talk about Newton's second law. Newton's second law. Now, Newton's second law, it talks about acceleration which is greater than zero, greater than zero, or less than zero, or less than zero. Okay, so what does it say? It says acceleration, the acceleration is directly proportional to the amount of force exerted to it. So Newton's second law talks about a resultant force. Resultant force. Okay. And it also states that the same force is directly proportional to the mass that the force is put on. Okay, now to summarize Newton's second law, this is Newton's second law. We're done. So you can just put that formula and you will get the marks. It's Newton's second law. That's Newton's second law. Okay, Newton's third law. It talks about action and reaction. It states that if the action and reaction, it states that whenever an object exert a force on another object, the second object exert an equal but opposite force. Yeah. Unlike in the Bible, if you hit one of my cheeks, I will return the same clap. That's what Newton's third law talks about. Action and reaction. If you clap me, I will clap you back. Newton's third law. Okay, let's do a recap. Newton's first law talks about a body remaining at rest or continuing to move. This is also called inertia. Newton's first law, inertia. Newton's second law, force equals ma. Newton's third law, action reaction. Okay, so I wanted to play you guys a small clip about Newton's law. Newton's law.
Newton's three laws of motion. Newton's laws can help us to understand how cars, bikes, and many other things move, even people. Let's talk a little bit about when we see them in everyday life. In simple terms, the first law, or law of inertia, occurs when an object remains still, unless something or someone moves it. The second law is used to explain why it takes less force to make a bike move forward than something that's heavier, like a car. And the third law of action and reaction happens when you throw a ball against a wall and it bounces. Every action, no matter how small or simple, has a reaction. Before exploring each of these laws, let's go over the meaning of motion, force, and acceleration. These three concepts are the key to understanding Newton's laws. We all know what motion is, when something goes from one place to another or changes its position. For example, as this duck walks, it's moving to a new place. But it also moves when it simply lowers its head to drink some water, changing its position. Force is when any action, such as dropping, pushing, or dragging, causes an object to move or change its shape. Joan wants to pick up the box that's on the floor and put it on the table, so she's using force. When she grabs the box and lifts it up, she's making the box change places. But if Joan's tired and leans on the box, she's also exerting force. Her body causes it to change shape. Lastly, there's acceleration. Acceleration describes when something like a car speeds up or when it slows down. Keep these three key words in mind as you learn about each law. Newton's laws of motion are happening all around us. They can help us to make sense of the world and to see things in a unique way. Check out our other videos to learn more about each of the three laws.
All right. We're gonna be continuing. So, what we know is that the Newton's there are three Newton's laws. Now I'm gonna talk about the resultant force, which was the topic I introduced earlier on. Now the resultant force the net of all the forces acting on an object. There must be forces acting on an object. Okay, let's say we have a box and there's a person who's pulling the box with a force of 5 newtons, and at the same time there's a toddler trying to pull the box backwards with a force of 1 newtons, obviously. Now the resultant force will be, remember we are dealing with vectors. Whenever we talk about vectors, there must be a magnitude and the direction. We have to choose the direction. Let us choose this direction as positive. You must always choose the direction. If this direction is positive, it means we will have 5 newtons plus, we are adding negative 1 newton. This will give us 4, this will give us 4 newtons. 4 newtons. Sorry for that. 4 newtons. That's a resultant force. Now, it can happen that you get forces acting at an angle on an object. Let's say, for instance, you decide to pull 5 newton. You decide to pull the box 5 newtons, and then the toddler also happened to be there, pulling it at a force of 1 Newton. If you happen to be pulling it, and let's say if the box weighs say 1 kg, if this is a 1 kg box, okay, first of all, in order to determine, let's say this is the ground and the ground is frictionless, let's just assume that the ground is frictionless. Okay, what we're gonna have is that we have an applied force which is at an angle, and now we want to resolve the resultant forces. We are dealing with 2D vectors. 2D meaning this two-dimension vectors. Your vector has a y component and an x component. In the example we did above, we were only dealing with the x components. We assumed that there was nothing on the y, but in a real world, there's always is. If this box had a mass, we assume that this box didn't have a mass. So let's assume that the box we are dealing with have a mass. If this box has a mass, what we know is that we have a resultant, we have force components. If we have a force which is tilted like that, we need to break it down into components. So that we can resolve it on the x-axis and also on the y-axis, because if it's tilted like that, we cannot. So let me isolate the 5 Newton. Now what I'm doing is called force projecting forces to the x and the y-axis. We are breaking down the applied force into components. If you want to break down your tilted force into components, you have to draw something like a box or a triangle, whereby this will be the components. This is component 1. This is the component on the y-axis, and there's a component on the x-axis. But in order to resolve this force component, what do? We have 3 forces, 3 components. Let us take all of them and build a triangle. Which one is the largest? Which one is the largest magnitude? The largest magnitude will be the applied force, and then I'm going to take the x component, and then I'm going to take the very same y component and put it there. Why am I allowed to shift it? We did an example. The first example, I indicated that all these forces are the same as long as they have the same magnitude and they are pointing in the same direction, they are the same. So what I just did here was just to move this force and take it to here. So we have a triangle. We have a right angle triangle. Let us try to resolve this right angle triangle. Now, in order to resolve it, we have the following. This will be 5. If you don't agree with me, you can go to the comment section. This is 5, and we have an angle theta. Okay, we have an angle theta. Okay, let me treat this as an applied force. Let me just say this is an applied force. Now, if this is an applied force, this will be the component of the applied force, which is a y component. We have a y component and an x component. Okay, let us go back to maths grade 10. Do you agree with me that the sine of theta is given by Fy over F? If you don't agree, please go to the comment section and say so. And do you also agree, because sine of theta is given by opposite over hypotenuse, and then the cos of theta will be given by Fx divided by F. Now, do you agree that the sine I think you will agree with me. I'm trying to extend what we have. I think you will agree with me that sine F or y is given by F sine of theta, and F x is given by applied force cos of theta. Now, always put this in your mind when we are trying to resolve. So let's say, for instance, if the angle was 30 degrees, if the angle was 30 degrees, we will have the following forces that we had to resolve horizontally. Okay, I'm gonna open another blank page. It's okay. So what we know is that the component, the x components. Let us deal with the x force components. What we know is that the resultant force will be the y component, will be the x component of the applied force 5. The applied force plus the force of a toddler. It will be the force of the toddler is a -1 because it's acting in the opposite direction. If we choose that direction as positive, then it will be plus, sorry, the force of the toddler is it's a -1. But the force of the applied force, let me start with the applied force. The applied force will be the x component of the applied force will be 5 times cos of 30 degrees, then plus the toddler's force is a -1. This will be, let's see, this will be 5 cos of 30. Let me get the calculator. 5 cos of 30 -1 to be 3.33, to be positive 3.33. If it's positive 3.33, it means the resultant force is acting in that direction, newtons. Now let us resolve the y forces. The y forces will be, what is it that we have? We have the y component of the applied force. We also have a gravitational force. We also have gravitational force, and we also have the normal force. And let's see. We have the normal force and a gravitational force. So if we are given that normal force in this case, it will be hard for us to solve for the normal force. Let's just assume that the normal force, normal force is about, say, about 5. Will 5 be enough? Yes, let's just assume that normal force equals 5 newtons. It means the resultant force in the y direction will be, let's choose upwards as positive. If we choose upwards as positive, it will be positive 5. It will be the normal force plus gravitational force plus the y component of the applied force. So we're going to have 5 plus your gravitational force will be 1 kg times 9.8, which is your gravitational acceleration, because force equals ma. In this case, our acceleration is gravitational acceleration, and our mass is 1 kg. So because this force is pointing downwards, it is a negative, plus Fy will be 5 sine of theta. So let's see how much we have. Okay, 5 plus 5 sine 30 minus 9.8. The answer is minus 2.3 newtons. What does it mean? It means the resultant force is downwards. The resultant force is downwards. Okay, let's move forward and talk about the typical forces that you're gonna get in the exams. Okay, forces. These are the typical forces you're gonna get in the exams. You're gonna get, let me draw a free body diagram. Free body diagram. You always gonna be asked to draw a free body diagram in any exam. Okay, these are the common forces. You're gonna get a normal force, gravitational force, or Fg. You're gonna get an applied force. As a result of the applied force, there's usually gonna be friction. That's friction. Okay, these are the typical forces you're gonna be getting. And when there's a tilted force, you must break it down into components. Okay, now, all right guys, I'm going to talk about universal law of gravity. Universal law of gravity, as the name universe explains itself. So we're talking about something that applies universally. So the Newton's universal law of gravity it states that every mass attracts another with a force directly proportional to the product of the masses of two objects, and inversely proportional to the distance between the centers of the masses. Okay, he also came up with a formula okay. So as you can see, that formula explains everything about universal gravity law, and G is called the gravitational constant and is given by 6.67 times 10 to the power minus 11 newtons meter square kg to the power minus 1. Okay, and of course your D is in meters. Okay, now there's often a confusion. A lot of students have come to me, they ask me, okay, does that mean I'm actually attracted to the person sitting or standing next to me? The answer is yes. Scientifically, yes. It is just that the force between the two of you is significantly small, that it doesn't do anything. You won't see it, you won't feel it. The bigger the object, the bigger the force. So if you talk about Earth is an object and it has a very big mass. So if it has a very big mass, it means even the gravitational force will be significant. If you go to Mars, it is the same thing. You will be attracted to Mars and Mars will be attracted to you. So we're gonna talk about the influence of the bigger objects. So what do we know and what we have been teaching each other is that if you put a box, it will have a gravitational force of attraction. And the surface of the earth, if you put a box on the surface of the earth will exert a normal force. And if you check, your force of gravity and your normal force are the same. They are equal. This is where we talk about Newton's third law. Action and reaction. The box exerted a force on the earth and the force exerted a normal force on the box. It is always like that. Wherever there's an action, there's a reaction. Newton's third law. Now, if we go to Newton's second law, the resultant force is actually zero. That's why the box will just stand there with no motion. Okay, without much waste of time, let's talk about the acceleration of an object. If we have an object, let's say a box, with a mass 0, and Earth, which has a mass of an Earth. Okay, the two will be attracted to each other with the same but opposite forces. That's okay. The acceleration of the smaller object will be given by force over m. This is Newton's third law, guys. Let me remind you, force equals ma. Then I made acceleration the subject of the formula, and I ended up having this. If you don't agree, please go to the comment section. I will explain it to you. F equals G This is the universal gravitational law. So do you agree with me? If I take this larger F and replace it in my initial formula, I will have a acceleration of an object equals to g m0 m of F divided by d squared. D squared times m0. This m0 is coming from here, and this m0 will cancel m0, and I will have g mass of Earth all over d squared. Okay, so this is the typical formula. So this also applies for an object which is in mass. So if an object is in mass, you're gonna have that. Your gravitational acceleration on mass will be given by that formula. The same thing as if I'm the host object. Let's say if I'm hosting, let's say if there's a fly on top of me, it means the gravitational force of attraction will be given by this formula. This will be the mass of me, and the distance will be the distance from my center to be the radius of my body. But that's okay. Let me highlight this formula. You're gonna need it. If possible, cram it. If possible, cram it. Now, what happens if we have an object and Earth? What we know is that Earth has a significantly larger radius, to a point where when we do our analysis, the distance between the object and the surface of Earth is often neglected, but up to a certain extent. But usually it is neglected. If we think about the gravitational acceleration scientifically, it can't be the same. It shouldn't be the same. It shouldn't be the same. If you jump higher, it should be different from when you are on the surface. There's a little different, but that difference is negligible. So the distance between the surface of Earth and the object is usually ignored. So the d that we use to calculate the gravity, it's simply the radius of Earth, or the radius of the planet. Okay, and it has been calculated for Earth. It has been calculated to be 9.81 meters per second. But I think in our syllabus, we're gonna use 9.8 meters per second. So that's about it. If you have any question, please go to the comment section. I'm done with our very nice lesson of universal gravity. Cheers.